So let's then continue with 1 second. Yeah. Let's just then continue with what we were doing. Let me just think. Do I want to tell you this or not? No, I don't think today we go here. Okay. Okay. So I would like to make today, I will hope that in half an hour we will go to the quantum problem and start thermalizing. But maybe we won't. Maybe it's going to be tomorrow, because I realize there are a few fun things to say about this model that it is perhaps worth spending some time. Okay. So here, so this is what we have seen so far. We have this stable model. And let's first of all notice that for the purpose of what we are going to do, it might be convenient to rescale these fields. You see that in the end, what really is interesting is this effective mass, which is the inverse of a correlation length, right? I can say that this effective mass, since it multiplies a distance, it's very natural to call it an inverse of a scattering length. And that's really the interesting parameter. And it's a complicated combination of all these constants. Not complicated, it's a simple combination of all these constants. It's in fact just this omega squared divided by kappa times some number. And here there are many constants, but we can set some of them to 1. In other words, physically, once you have too many constants, it means that you are not measuring things in dimensionless quantities. So it's always convenient to eliminate one of the constants if we can. So we could here say do a rescaling and in the tutorial you are invited to work this rescaling out. So I'm just going, so let's just write what we will find. After we rescale, let's call the variables y after we rescale, just so that we are not confused. X is alpha times y. And I rescale in a way that in terms of this variable y, this will become the following, sum over n. And I want here 1 over 4 without any kappa and any beta. So that's what I absorb by sum over L y minus y squared plus, and then here it will be automatically rescaled. And let me tell you what you will find here, and you can easily check. M effective square over 2 times yn square plus some coupling. Okay, let's call it something else. G, which is just this guy rescaled, times yn to the power 4. Okay. So why was this a clever thing to do? Because now you see beta times k became 1/2. Beta times k sorry, there was no m squared here. It was just m. Sorry. And here there was kappa over m. Yeah. Okay. So beta times k became 1/2. So this became just a 4. And therefore, when I expand this at small k, this thing here in this new rescaling just became k squared. That's why this is a clever normalization, to put this 1/4 here. Right? So again, beta times k is 1/2. So the 8 becomes a 4. When I expand out at small momenta, I cancel the 4 and I get just k squared. And therefore, whatever remains after this rescaling is what we call the M effect, because it's what we add to k squared. Okay? And therefore, that's what you would get here in this term with this M effective over 2. Okay? By comparing. And then there is this coupling G. And now what's important to notice is that the temperature is here. So saying that we move the temperature now would be moving this parameter G here, because we absorb these Y's. And Y's behave in the same way. They have the same kind of propagators, and because they are just rescaling of the X's. Okay. Now, let me just make I would like now to make a few comments, which is that about some generalizations and universality. Okay, so a few comments. So first, we had some potential for y that we chose, which was this m effective square over 2 times y square plus mu y to the 4. Right? So this was the potential that we have there, and that's a potential like this. And here, in this bottom of the potential, the second derivative of the potential is this effective mass square. So the first comment I want to make is that this is general. Right? So if, for example, my potential would be something like cosh hyperbolic cosine of y, say -1 to be normalized at 0, with some beta and I don't know, some overall alpha, for example, right? This would be equal to alpha, and then when I expand this out, the 1 cancels the 1, and I would get beta square y square over 2 plus higher terms. And therefore, when I take the quadratic term to read off my free propagation, to read off my propagator, my free theory around where I expand, from here, for example, I would read off the effective mass square would be, in this example, alpha beta square. And this potential here, of course, is also a potential like this. And what happens is that you create some excitations at the bottom of the potential, and the excitations move back and forth in this potential. And the derivative of the potential is related to the mass. Very heavy particles want to stay close to the bottom. That's when the potential is very thin. When the potential is very shallow, they don't mind fluctuating. Right? So lighter excitations fluctuate more, of course. Lighter excitations fluctuate more. So in the same way that here we had our free term, and then we thought of this as an interaction. Same here, if we are close to the minima, y is small, and therefore these higher powers are more suppressed, so this would also be interactions. Okay, and as usual, I'm writing here that you cannot see. Good. Now, good. So we could also wonder, what about this m square negative for mu positive? So if m square is negative and mu is positive, the potential that you would get would be something like this. Right? So now, if m square is negative, right, you just put a minus sign here, and now the first derivative is negative, and it's the mu term that eventually kicks in. So now you have two minima. Okay. So this means, so it's like so there is some, this is our table, right? And this would be y equals 0. And this would be a displacement. This would be y equals 0. And this would be a displacement that the table would prefer. So let's see. So what are these positions here? Right, so I compute v prime equal to 0. So I would compute my potential. I would get m square, I remind you, this is negative, times y. Let me call this y star, the position of the minimum, plus 4 mu y star cube. So y star is square root of minus, which is fine because m square is negative, m square over 4 mu. And therefore, what our table does, the table wants to go to this position y star or minus y star. So there are two stable equilibrium positions that our table would like to go. Okay? So it could be, I don't know, you are stretching your drum and it's like a thin layer of metal and it likes to bend like boom or boom, you know, this. Can you imagine this material that you hold and it likes to go slightly up or slightly down? It doesn't like to be exactly at 0 because there's some tension pulling. Okay, so there would be two stable vacua, but in the presence of this tension, being exactly flat at 0 would not be as good as being slightly up or slightly down. Okay, so this could be a toy model for that. So then our material prefers, so this would be preferable to being at y equals 0. So this is something we could have done in our code when we were thermalizing the table. We could have flipped the sign of the mass, right? And then we hit the table, and the table could end up in one of these minima. Okay? So how would we typically choose which minima? For example, with boundary conditions. If what typically will happen is that what we would imagine happening is the following. So if at these boundary conditions we say that y at the boundary of the table is equal to plus y star, right? We fix it to be y star all over, then typically the full table would go to y star. Right? For example, this would be the idea that if we choose this, then the question is whether this happens, that the table goes to the plus y star vacuum. That's one natural idea that this could happen, right? Because there are two vacua that are equally likely, and you fix the boundary to be at the plus vacuum. So the natural thing is for the full table to go to that vacuum, right? It's like she doesn't know which one to choose, and you said, okay, this one is better at the boundary. Or another thing we could do is to our action, so to our to our action, we could transform into action plus a sum of some pressure times yn, where this is like some pressure that would tend to favor, now depending on the sign, so I put P, and then we take P finite, and then we take P to 0 plus or 0 minus. And the idea is that if you put some pressure right there, you are choosing which vacuum is better. Because once you put this pressure, right, once you put a linear term like this, you are lifting your potential. Now one vacuum is better. Right? So now you chose this vacuum, say. Okay? So now after you put this pressure, the degeneracy is lifted, and therefore you expect to go to that vacuum. Sorry, yeah.
Sorry, what are 0 plus and what do you mean by 0 plus and 0 minus?
You go to 0 through positive numbers or through negative numbers.
Oh, oh okay.
So the idea that you first put some pressure, which means you push the table in the direction to go to one of the vacua, and then you turn it off, and it will stay there. Or you first push it up, now it goes to the up vacuum, and then you turn it off and it stays up. So the idea would be that we take it to 0 plus, we end up in one vacuum. End up in one vacuum after we turn P off. And if we take it to 0 minus, we end up in the other vacuum. Okay? So here I'm just telling you expectations, what we would expect naively, just like hand waving, and this would be our expectation. So soon, now I will try to continue with these general expectations, but at some point in the lecture we are going to see, is this reasonable or not to expect? Okay? For example, I'm going to tell you that we could do this table in any dimension, right? And we could ask, is it true that in any dimension that's what happens if I fix the boundary conditions and I have this vacuum, that it would choose to go to one of the vacuum. Okay? And we will see that it is true in d bigger than 2, but if it is one dimension, it's not true. Okay? So that we will see soon.
Yes. Is it physical to have m squared less than 0?
Yes. It just means this potential. It just means that it's a potential like this. The fact that we call it m then makes us confused because we say, oh, m cannot be negative. Or m, but it's just the potential, right? By m negative, I mean this. I mean.
Okay, so you don't mean the effective mass.
So what happens when m is negative is that if you think that you have an excitation here, this excitation is unstable. Excitations don't like to be here. They like to be here. Right? So expanding around x equals 0 is a bit silly. We should, in this case, be expanding around this position. And then the mass would be the derivative at this point, and not the derivative here, right? So at this point, the mass would be the curvature of the potential at the minima, at the new minima. And what would be reasonable is to expand around that minima, right? But here, it would be m squared equal negative, which is what we call a tachyon, which is just an instability. It's just saying that you start here and you will roll to the other guy. So the fact that m squared is negative here just means that this point is unstable. Then we go here, where m squared is positive. Now, what could we expect qualitatively to happen to such a table when we have these two potentials? Right? So let's imagine that we have here a region where we are in the plus vacuum, and then a region where we are in the minus vacuum, right? And we could have here some bigger region where we are in the plus vacuum, and inside there could be two regions, say, where we are in the minus vacuum. By this, I mean that here we have, if we follow y here, right? Remember, we had y star, we had minus y star, and we are following y in this region, and y is here fluctuating around the value minus y star. Right? And then, if we plot, say, what is y along this line here, so we are here, we are moving here, it's fluctuating like this, then we hit this point, and at some point, y would be fluctuating. After this point, this is A, this would be A, then it would be in the plus vacuum. And then we propagate further, and at some point, it's in the minus vacuum, fluctuating there around the minus vacuum. Okay, good. So here, we are in the vacuum. So here, in this piece, the energy is some E0, some vacuum energy. And here as well, the same vacuum energy. Here, the energy is at some E0, or by maybe we should say energy density is at the same E0. Right? But here, at the wall, there is an energy cost. There is an energy cost at the wall. So what is this energy cost? This energy cost comes precisely from the fact that we have interaction there between the y's. And now, at the wall, when we have a wall, we have y n minus y n plus L square. And this is in the vacuum plus, say, and this is in the vacuum minus, right? So this is equal to 4 y star square, right? So it's y star minus y star is 2y star. I square it, I get 4y star square. And therefore, the energy cost of the wall is what? Is 1/4 at one side at the wall. So the energy square at one side of the wall. We can estimate it by saying, well, there was a 1/4 there by normalization. And there are two terms like this, because there is this neighbor and the neighbor going opposite, right? So we have the two sides that are involved at the link, at the, sorry, side, no, at a link. So I say I have a separation here, and this side couples and this side couples, so there is a factor of 2 as well. So there is a 2, a 1/4, so it's this times 1/4 times 2, which going back to the previous parameters we had there, it is minus m squared over mu, which I could call beta j. And that's my definition. Yes?
In this case, is L some small separation across the wall, or like what are yn and yn plus L?
Sorry, n plus L. L, remember, were the neighbors. We were summing over the neighbors, up, down, and so on. So now I'm considering this is the wall, and this here is the vector L that connects the two neighbors. And one is in the plus vacuum, and one is in the minus vacuum. Now, if they are both in the same vacuum, this is 0. Because this is y star minus y star. Right? So this is equal to 0 at the same vacuum. At the vacuum, they are constant. Right? So they are constant, so if there is no variation, this doesn't cost any energy. But when they jump vacuum, this is in the vacuum plus, this is in the vacuum minus, so this is y star, this is minus y star. So I now have a diff.
Can you explain the 2 and the 1/4 again?
So the 1/4 is because it was there. There was a 1/4 in the Lagrangian after we rescale. And the 2, it's because we sum over sides. So this side couples here. But there is another term when I sum this side which couples there. Huh? You see, we sum over all sides. And there are 2 sides involved in that link. The one side of the link and the other side of the link. So that gives a factor of 2. Yeah. So that's the 1/4 is there. The 2 is the 2 sides involved in the link, the 2 ends of the link. The 4 is just 2y star squared. Okay, and we call this beta j. Okay, that's my choice. So you see that this model bears some resemblance. It looks similar. A toy model for this table. Could be to say that at each site n, we just have a variable sigma n. Actually, sorry, let me define it like this. This energy cost, I want it to be 2 beta j. That's the definition of j. Okay, and at each n, I have a sigma n that can be plus or minus 1. And this just indicates which vacuum. In my original table was which vacuum. Is the table slightly up or slightly down? And then in this case, what would be my effective partition function? Right? It would be I just sum, and at each side, I sum over the sigmas that can be plus or minus 1 at each side. Right? So there are, in this sum, there are 2 to the L squared terms. Right? Because at each side, I say if it's plus or minus. And then I would have just e to the minus beta, and then j, and I sum over neighbors, I and j, where these guys are neighbors, sigma I, sigma j. Right? And this will have exactly the same property I have. I now just specify at each side if I am in the up or the down vacuum. And then the neighbors, when, sorry, let me delete this. Let me put a constant, minus 1, say. So when they are in the same vacuum, this link gives 0. But when one is in one vacuum and the other is in the other vacuum, it costs beta j. But we sum over all pairs. So here we are summing over the links. Beta j, so when they are opposite sign, when they're opposite sign, you see, minus 1 gives me 2. Okay, so that's the 2 that I wanted to define there. Right? So this has exactly this property. I'm now summing over just configurations, and I am saying that in my lattice, I have some region in my lattice where sigma is equal to plus 1, and some region where sigma is equal to minus 1. And the energy cost for each of these links is 2 beta j for each link here that separates this region. Right? So this would be the energy cost at each of the links. Now, it's kind of amusing because this model, we could think of it coming from a totally different thing. This looks like some kind of spin system. We start with a table, but this could be a spin system where we have a bunch of magnetic molecules, right? We have just a lattice where at each lattice I have some molecule with some magnetic spin. And they could interact, and that term in the Hamiltonian would be some kind of spin-spin interaction that would want to align or to anti-align the spins. But as I'm zooming out, I'm expecting that, okay, these fluctuations are a bit irrelevant. What matters is whether they are down here or up here. And this toy model should describe roughly the same physics as that table. And indeed, the claim is that this spin system and our two-level table are in the same universality class. We don't need to study both models. If we care about long distances, they are the same. They have the same long distance physics. Let's see. So you are saying that here, when they are opposite, it costs some energy. I think it's okay, no?
Well, the energy cost should contribute with the negative sign, right?
So, yes. Good, thank you. Yes. Yes, good. So you see that when all spins are up, this is 0. Whenever one spin is down, it's more suppressed now. Right? Because we flip a sign and we get a negative sign, as your colleague said. So the idea would be that as I'm zooming out, whether I have just constant spins 1, constant minus 1, or I have a table that is small fluctuations around 1 and then small fluctuations around minus 1, should be the same thing. So these models will be in the same universality class. And at large distances, what is interesting is what is the dynamics of these regions where the table is up versus when the table is down, or when the spin is up versus when the spin is down. And that's a very important notion. This is this notion of universality, that from far away, two very different systems could be exactly the same. Okay? In fact, notice that if we kept the pressure term, that I wrote here, that couples pi p with y, I would get, if I keep this term here, if I do add this term to my table, this would correspond here to a term minus beta h times sum over sigma I. And this would be, we would think of this as an external magnetic field. So what would be the pressure, now we would interpret as a magnetic field that would tend to align or anti-align the spins. To put them up or down. Notice also that we could also, now that we are at this toy model, we could define sigma I to be twice ni minus 1, where ni equal to 0 or 1. This is just the same thing. And now our partition function z would be something like, I would sum over now these positions n. Okay, now I don't want to use letter n for the position. Okay, or maybe I do because it's fun. Okay, n, that would be 0 or 1. So the n vector is a vector, the other n is just 0 or 1. And then up here, let me write e to the minus beta U sum over Ni and J over neighbors, Ji minus beta mu sum over the Ni. And now I could interpret this as saying that I have a gas of particles and at each side I can have no particle, which would correspond to n equals 0, or I could have one particle that could correspond to n equals 1. And then we would sum over configurations where there is a nearest neighbor interaction on this gas, and where this mu would now play the role of some chemical potential that would put some energy cost to having many particles there in the gas. Okay? And so this spin system and this two-level table and this fluid or gas are all in the same universality class. And if we know how to describe one of them at large distances, we would be describing all these models at once. Okay. And now we ask whether this is all correct, right? By this, I mean the notion of order and of this two vacuum stuff. This idea that there is this order and that we pick a vacuum and so on. So the question we want to ask is the following. Suppose I start with a configuration where everyone is up versus a configuration where some guys are down. Right? And here you could imagine that you fix at the boundary of the table everyone is up, right? So you would imagine that everyone would like to be up inside. But the question is it true, or is it better to create a bubble inside with minus? Is this favorable? If so, the table will not go to the other vacuum, but rather will start creating all these bubbles. So which configurations dominate? Now, these ones here are more energetic, but, however, very importantly, they have much more entropy. Because for a given boundary L, there are many ways of choosing this boundary. So I need to be careful seeing who wins. Is it the energy? If it was just the energy, it would not want to create these bubbles because they cost energy, it would suppress. Or is it the entropy? Because there are so many options that the entropy wins. Okay? And here we have to be careful. So, right? So we ask here, who wins? So let's start with one dimension. Well, in one dimension, we have a line, right? We have our sides of our table. And what we want to ask is, can we form some big domain, some domain minus, where this domain has some order of some big size d? Well, what's the energy cost? there are two walls which cost energy, right? So there are two walls that cost energy. So we have each energy cost was twice. So we have 2 beta j. That's the energy contribution. But then we have the entropy minus, or let's put minus here and plus the logarithm of the density of states. So then we have the entropy, which is something like log. And then we have to choose where to put these walls when the size is of order d. Well, there are d options for this wall, d options for this wall. So it's something of the order d squared. Right? So this is d options roughly about d options per wall. That's the entropy for creating some big chunk. I choose where to put this wall, where to put this wall with some, say, L over 4 freedom, L over 4 here. So d over 4, d over 4. So it gives me something of order log of d squared. D options for one, d options for the other. So we see that this is much bigger than this. So this always wins. This always wins, which means that in one dimension, we will not spontaneously break the symmetry and choose one of the vacua. So it is not true that if we think of our model in one dimension, there are two vacua. We could think now that if I put some boundary conditions, everyone would like to go to the up vacuum. But no, because what happens is that we start with everyone up. But then these configurations dominate, which let me draw like this. There is a red line, and then a green segment, and then a red line. So these ones are better. So even if I fix the endpoints to be plus plus, it's better to put some puddles of minus. This dominates. And of course, this is just one, but even better would be to start putting many puddles, and inside the puddles more puddles, and inside more, then more, and so on, etc. This would be even better. And therefore, if we look at our material, what will typically happen in this magnetic one-dimensional material is that even if there are two vacua, even if we have a table which would prefer at 0 temperature two vacua, as soon as we turn on the temperature, it prefers to randomly fluctuate between the two vacua, and it doesn't support order. So unless beta is infinite. So what we conclude is that order is impossible at finite temperature. In one dimension. Right? So again, in terms of magnetic materials, you start with a magnetic material and you put some magnetic field. So the spins want to go up, and they go up. Then you turn them off slowly, the magnetic field, and you could think that since that is the ground state, it will stay there. All spins will be up. But no, they prefer to create some up, some puddles down, some up, some down, and you would look at large distances, and they would not all be up. Okay, and similarly for our table, that now would be a spring. Yes?
Okay, so the quantity you're computing over there, minus 4 beta j plus log d squared, is that just the difference between?
That's the competition between the energy, which is the first term, and the entropy, which is the second term. So I'm computing the free energy variation due to going from one configuration to the other. Right? So we are summing e to the minus beta energy plus log of entropy, right? So we are computing the partition function. So we have, remember that my partition function is I integrate over the states e to the log of the entropy minus beta energy, right?
Okay.
So this would be log of entropy, and this is beta energy. So we ask whether compared to in the vacuum, there is no energy and no entropy, nothing. Compared to the vacuum, this is better because this has lots of entropy, and the energy is suppressed, but not as much as the entropy is big.
So you're trying to maximize.
So these guys contribute more to the partition function. They dominate the partition function, right? Because it's the free energy. So this partition function would be E to the minus the minimum of the free energy. Remember that this free energy was computed by saddle point, and it was at the minimum that dominates. So whenever we have some configuration, because we are dealing with such large values, it will choose to find where is the equilibrium between the entropy and the energy. Remember, that was the definition of temperature when we found what's the equilibrium condition, right? So now we are trying to find an equilibrium to see what does she prefer. And we see that the free energy prefers to just put more and more puddles. It doesn't. There's no advantage in fixing, in suppressing them. Now, in 2 dimensions, it would be different. Now, in d bigger or equal than 2, there can be order. Okay. And I will explain now for d equals 2, but the argument for d bigger than 2 is similar. So let's check for d equals 2. For d equals 2, now we have some domain. And let this domain have length L. Sorry?
The length is
the perimeter, yeah. So let this have perimeter L. So what's the energy cost of this configuration? Well, at each side of the perimeter, I have 2 beta, right? So it's 2 beta at each side, and there are length L. So now so it's minus twice beta J times L. That's the contribution to the free energy from the energy. Now, what about the entropy? How many paths are there that encircle some domain which have length L? It's hard, actually. It's not easy. So, but we can estimate. So let's estimate. Okay. So it will be plus log of the number of paths of length L. Okay. Now, notice that these paths, because by definition, these are non-intersecting paths. Right? They don't intersect. So this number of paths at length L, and this L is large, so we are going to write now asymptotic formulas. So let's call this omega L. And then this omega L is definitely smaller than 3 to the L. Okay? Why? Because what is 3 to the L? 3 to the L is the following. I start at one side, and I start doing a path, and I go here. And now I don't want to self-intersect, so I have 3 options. Right? So I choose to go here. And now that I'm here, I don't want to self-intersect, So I have 3 options. So I go here. And then here, I don't want to go back because I cannot self-intersect, and I have 3 options. So I say I go here. Right? So now you see here, if I say 3, I'm lying. It's actually 2. So, and furthermore, it has to close. So these are paths where we do not go back. And they are certainly much bigger than what we call self-avoiding walks. So this is paths that don't intersect. Self-avoiding walks, right? Because self-avoiding walks definitely cannot go back, but it's much more restrictive because, for example, here I cannot go here. And furthermore, they even have to be closed, right? So definitely this is a bound. But now I'm going to say that this is much bigger. So this is e to the L times log 3. But now let's see that on the other hand, this is much bigger than e to the log 2 over 4 times L. Okay, that's what we are going to see next. And therefore, once we establish this, we would claim that this omega is some kind of mu to the L, where mu is a number between 3 and a 4th root of 2. Okay. Where this is a number that is somewhere between these 2 exponentials. But we would not know what it is. So let's just establish the left-hand side then, and then we will be done. So what we want to do is to construct an exponentially large number of paths that encircle, that have length L and that are closed. So what can I do? I can say that I do first L over 4 steps, and at each step I just go right or up. And I do L over 4 like this. Right? So L over 4, first L over 4 steps, always up or right. So they definitely don't intersect, right? Because you just go up or left, so they don't self-intersect for sure. Right? How many there are? There are 2 to the L over 4 options, which is e to the log L, e to the log 2 over 4 times L, right? So that's exactly already what I have. So all I have to do is now to say that I have this path. Okay, so let me draw this like this, saying it's a path that goes from here to here. Okay, it starts from this point, goes to this point. So I have some path like this. And now, one path that has length L is obtained by copy-pasting this path. Okay. I just do copy-paste and rotate. Okay. So this I choose, and now these guys are just copies of this guy, and that will close. Okay. I just take this, I rotate it, so this and this are the same, reverse, and this is whatever it is. So here is a construction of a given number of paths. They are all self-avoiding and they all have length L. Right? But they are not all self-avoiding paths, but it's a big class of them. Okay? So we could do better. Instead of doing L over 4, L over 4, L over 4, you could improve the bound much more. You could do 9/10 of the paths like this, and then do some rectangles. So you can improve this bound much more. But it doesn't matter. For the argument, I just want to show that this number here is definitely smaller than the number of closed self-avoiding walks, which is what we wanted. So it's one way of doing paths that have length L. L over 4 each, so in total length L. And therefore, we conclude that our change in our free energy is minus twice beta J L plus L times log mu, where mu is a number between, where log mu is a number between log 2 over 4 and 3. Doesn't matter which one. And so now who wins, the entropy or the temperature? Well, it depends on beta. So now we see that if beta is bigger than some beta critical, the energy wins. And if beta is smaller than some beta critical, the entropy wins. So it means that even if we have our two vacua, now depending on the temperature we are effectively considering, we could either, if the energy wins, it will mean that all plus order is preserved. But if the entropy wins, we form domains and we don't preserve the order. And what happens is that as beta approaches the critical temperature, notice that, beta smaller than some critical temperature means temperature is bigger than some critical temperature. Temperature is 1 over beta. So this is high temperature, and there is no order. And this is low temperature, and there is order. Right? So this is the low temperature regime, and this is the high temperature regime. What happens as beta goes to beta critical? As beta goes to beta critical, the scattering length, which was the inverse of the mass, goes to infinity. And the typical size of these domains will become very large. And now we would have domains of all possible sizes. As the critical exponent would be, so the correlation length would diverge, and we would have fluctuations at all scales. Now, and this is also what happens in higher dimensions. Can I write here? Or do you prefer if I erase? Should I erase or write here? As you prefer. Who prefers that I write here? Who prefers that I erase? Okay. It's the same. I will erase and write there. Yeah. Now, another thing we could consider that would be another very interesting modification of our table. And that's what you are going to do in the tutorial, would be to consider a partition function where now you don't have 1 degree of freedom, but you have n degrees of freedom at each site. Okay? So this could be, say, the 3 dislocation, for example, right? X, Y, Z now. Or it could even be more. There could be more degrees of freedom. Like at each site, there could be some breathing modes or materials that could have different internal degrees of freedom at each site. So n could be 3, but it could even be bigger, right? So n now would be the number of degrees of freedom per site, right? And how would we generalize this expression now if I wanted to put an index j there? Right? So now let's try to understand how to modify these various terms in this table to introduce. Sorry, I want to make one more comment before. So the conclusion of the previous analysis right? So the punchline here is that when we have discrete symmetry, so in our example, it was a Z2 symmetry, right? Z2, it could be up or down. So when we have this discrete symmetry, we can have order in D bigger or equal than 2. And I want to emphasize that although we had some particular models in mind, it really was accounting of the fact that interactions are local and that the number of configurations is related to drawing loops or to just counting walls. So it's really totally general. It's not related to a particular spin system. Any model which has local interactions, and if I'm considering a big domain, the energy difference would be proportional to the length of the domain. The precise fact if it is twice j or some other number, of course, will change, but the basic idea that it's proportional to the length would remain. And also, it is not related to just a Z2 symmetry. If it was a potential with 3 wells, so if we would have some kind of Z3 symmetry, same story. It could be a potential where there could be 3 stable equilibrium positions, and now we could have some domains up, some domains down, some domains quiet, right? Some domains at position 0. And by exactly the same arguments, we could ask, is it better to create many types of domain? Or if I choose a boundary condition where everyone is at plus at the boundary, I still go all plus. And exactly the same argument would apply without any modification. Okay? Is it clear? For example, if there are n options, if there are n vacua, of course, when I compute the entropy, the main factor is the same. It is this mu times L. But I could say that the puddle inside could be of 1 over n minus 1 colors, right? But that would be just some factor that I will multiply. I would say there is this choice per n particles. So it will just give me an overall constant multiplying it. Do you agree? For the entropy, it will just tell me that for each type of puddle, I have the same computation. So what's important here is that there is a discrete symmetry and we have a some local model. And then we can have order in D bigger or equal than 2. It could be, for example, some Z3 symmetry, but we cannot have order in D equals 1. Okay? So you probably all solved the Ising model in 1 dimension, right? Did you? Did you solve the one-dimensional Ising model? Just spin I plus 1, and you sum? No? Okay, we'll do it next week. But if you did, you saw that if you compute correlation functions, they decay exponentially, and the correlation length is always finite. There's no point where the correlation length blows up and where we have a phase transition. And the reason is because it's 1 dimension. Okay, but now we are moving to a different setup where we have more degrees of freedom per site. And therefore, we would have to modify these expressions. And let's start with the easy one. So this one here, we would modify it and say that I have a yn component j square, and I sum over j equal 1 to n, right? So if this is the height, the x dislocation, and the y dislocation, I just have a restoring force in x, restoring force in y, restoring force in z. And I just sum the three components, right? Same thing here. Here, this term would be just the sum over j, y n j minus y n plus neighbor j square. So these two are more or less clear. And now this here, notice that I can write this as in the following form. I can make a vector y at site n, which has all the components y1 up to yn, and say that this is the scalar product between the two y's. And similarly, this is just, if I have the vector at position n minus the vector at position n plus l, this is just the square of this vector, or the dot product with itself, right? So you see that we have a rotational symmetry, which is of course clear. It's what I was saying. If I have these locations in 3 dimensions, what matters is the separation from the origin, right? So it is rotational invariant. So here we see clearly that there is some ON symmetry. So nothing changes if I change y into some constant matrix D of ON matrix times y. Because I remind you that D transpose D, if it's a rotation, this is just the identity. So this is a natural symmetry we could want to preserve, and we could want to study models that have this ON rotational symmetry. Then we have to be careful what we mean by this yn to the power 4. This yn to the power 4, if I write x to the 4 plus y to the 4 plus z to the 4, this doesn't have rotation symmetry, right? So what has rotation symmetry with x, y, and z to the power 4? How do I make something that has rotational symmetry?
X squared plus c squared plus the other one squared.
Very good, right? Did you all understood? It is just the distance squared, that is rotational invariant, and then I square that. Very good. So what I should write here is a summation from j equal 1 up to n, y j at position n square. That's just the norm of the vector, and then I square that. Right? And this is nothing but y dot y squared. Okay, and now we could again ask, and I will not thermalize my quantum table today, but okay, it's fine. So we could ask again now, what's the kind of physics that we expect for this model? What physics do we expect? So what do you expect if the m square that appears in the Lagrangian is positive? Well, then it is just a table again, right? It's the same physics of the table, except that instead of having just height, we have height, left, and width and depth, right? So we just have these locations in the 3 possible directions. But if m square is positive, now I'm thinking of some kind of potential that is now an n-dimensional potential, right? But now my potential, this would be, for example, my potential V, And this would be a picture that I could draw only if n is equal to 2. And this, in that case, would be the component 1 of y, and this would be the component 2 of y. And what would happen is that they would just want to fluctuate around here. Right? And that's indeed pretty clear. That's what happens if I draw the quartic terms to study what is the propagator. Who cares about the fact that I have j? It is just j decoupled models. You see? It's exponential of the sum over j of the Lagrangian for one table. Right? So for each mode, j, it is just the same exercise that we did before with the same m effective. Everything is the same. What about two different j's? Two different j's don't talk to each other, right? Because it's just two decoupled modes. And therefore, for example, the correlation function between a yi and the yj at position n and at position n plus x would be just delta ij times the integral d, let's do d dimensions, d dk over 2 pi to the k e to the minus I k dot x divided by k square plus m effective square. Okay. And that would be the propagator. So this is as mu is equal to 0. On the other hand, if m square was negative, now the potential would be quite different. Now what would happen is that the potential would be like a Mexican hat. This part would be flipped upside down now, because close to the origin the quadratic term is negative. And there would be a valley here of minima. So now here there is a continuum line a continuum valley of minima. Right? Because if I compute my potential for some field which has some radius r and then some unit vector n, this would be unit, some unit vector, what do I get? I get that this is just m effective square r square over 2 from the quadratic term, and then from the mu term plus g r to the 4. So it's exactly the same Mexican hat potential as before, but it's true for any unit vector. So it then draws a circle, which is the valley. Okay. So now, instead of plus minus vacua, now we have a continuous family. Which is given by the choice of this unit vector n, which is given by saying where in this potential am I pointing, for example, to this point in the valley. This would be one vacuum. Okay. And now we want to ask about what do we expect now for the phases of this model. So do I expect now to have a table? And here, at the boundary, I fix the same n. So I point in some direction, right? Or if you want, or add some symmetry breaking term, which would be like the pressure or the magnetic field. So some symmetry breaking term, that would be now something like a vector pressure dotted with some y, right? And that will tell me one direction now is preferred, right? And then turn it off. That's roughly equivalent to putting a boundary condition where they are all pointing in the same direction everywhere. Now it's not just up, down, it's a continuous vector. And the question is then here, do I prefer to form vectors pointing in another direction? Because these are also good vacua. Right? Do I prefer to form these other puddles of vacuum or not? Because before we saw that sometimes not, depends on the critical temperature. There is a temperature where it's better not to create domains and another temperature where it's better to create domains. Right? So we ask again, here, who wins? Energy versus entropy. Now for the entropy, the computation is roughly the same. We have some domain, there is some path, and therefore the entropy will still be given by L times log mu as before. This is just from counting the paths. But now the energy, however, we could imagine that we have some very dark region where the vector is really pointing in this opposite direction. We have some white region here where the vector is pointing in the other direction. And we could have some transition region now. So let's say that this region could be, I don't know, something like L over 10. I don't know, some fraction of L could be used to transition smoothly from one region to the other. Right? So you can imagine that this arrow is like a color. So pointing there it's red, pointing there it's blue, but it changes gradually from red to blue. So what you would see is a blob whose boundary is blurry. It's not really red and then blue. It's red almost everywhere and then violet. Then okay, follow the rainbow and then right. So it would change smoothly. So this would be like some transition, and this would be some transition region. Right? So here, notice that it's key that we are dealing with a continuous symmetry. If it's discrete, there's no such thing as changing smoothly. You just go and change. Right? But now we can change smoothly. So what happens is that here the vectors change smoothly. And they start like this, and they end up at the end like this. So in the middle, they change smoothly. Right? From one position to the other. So what's the energy cost now? Well, now at each transition here, each little bit costs some energy, which is the y at position n minus the y at the neighbor. But by how much do I need to change? If I have like L sides to change, or L over 10, if I have of order L sides to change, at each side I just need to change by 1 over L. right? At each side, the vector is similar to the other one by 1 over L, right? Sorry, very bad notation. This L is the length, and this L is the neighbor, right? So let's put here n plus 1, right, to indicate it's the neighbor. It's not the vector, okay? And then it's the square, right? So this is proportional to this, but this is proportional to 1 over L square. Do you agree? Because now the spin has L units to change. So the derivative is of order 1 over L over length L, so that the integral of the derivative is order 1. Right? It's clear? The function changes L times, so its changes of order 1 over L. So we have 1 over L square. And what's the volume? What's the area that I integrate over? Well, it has a length L and a perimeter L. So this transition has an area of order L square, which is just the width times the perimeter, right? And therefore, these two things together, the area is of order of square, and the energy density, so this is the energy per area, per unit area, or energy density. The energy density is 1 over L square. The area is L square. So in total, the energy cost is beta J times some finite amount. Right? 1 over L squared times L squared gives me finite. And therefore, the contribution is that the entropy always wins. And that's the statement that in 2 dimensions, we cannot have spontaneous symmetry broken. So here, we had some model with ON symmetry, and we were saying, but will this symmetry be broken spontaneously? Will the model choose one direction and be there? Well, so of course it will choose, because we will push a little bit and it will go there and break the symmetry and go to a particular end that breaks the symmetry, right? That would be what we call spontaneous symmetry breaking. Okay, so spontaneous symmetry breaking is the fact that I start with a theory that has ON symmetry. So I start with ON symmetry. There is, however, a vacuum, and if my field Y, if I can say that it's equal to N times some R star plus delta Y, this choice of this particular vacuum breaks this ON symmetry. Like when I had before the Z2 symmetry, so things were invariant on the plus minus. When I choose plus, I'm breaking the symmetry. So this would break ON. So if my Y's chooses to break this symmetry, we say that we have spontaneous symmetry breaking. And that would mean that we would have order would be preserved. That is, we could consider a domain where everyone is up, and that would be okay. Here we see it's not okay. Even if I start with everyone pointing in the same direction, let's call this up, around, it's always preferable, entropically, to create domains where they are pointing in other directions and they vary slowly. So it's not possible to have long range order if you have a continuous symmetry in 2 dimensions.
What order is preserved here?
The vacuum, saying that I have a material and like a magnet, for example, in 3 dimensions, and the magnetization is pointing in some direction. So there is magnetic field, there is a magnetic moment across one direction, right? Now, And that's there over a macroscopic piece of material, right? So why did the spins in a magnet shows one direction and not another one, right? In nature, things are rotation invariant. So in the material, things were rotation invariant. But what happened was something like this. So there was a rotation symmetry, but symmetry was broken, and they chose randomly because you pushed some magnetic field when you were constructing the magnet or whatever, and now it's pointing in some direction, and it's preserved. You take a big magnet, right, and the magnet works. There's some magnetic moment in one direction, right? A big magnetization. But that's because it's three-dimensional. If it was two-dimensional, this could not happen. Because in 2 dimensions, even if you start with a big domain where all spins are pointing in the same direction, if they could rotate smoothly, they would prefer to rotate and disorganize. They don't like to be ordered. Ordered would mean that they are all pointing in the same direction.
I don't understand what's the difference between 2D and 3D.
So I just did the counting of the fight between entropy and energy. We did it in 2 dimensions.
But for 3D.
For 3D, I did not do it. I did not do the computation. I'm just saying that if you did it in 3D, the entropy and the energy could compete with each other, and you could have a phase transition, and you could have order. So you saw that in the previous case, in 1 dimension, you could not have even discrete, right? But in 2 and higher, you could. If it's continuous, both 1 and 2 you cannot have, and 3 and higher you can. Right? So continuous kills 1 more dimension. So discrete, it's just 1 dimension that you cannot have, and continuous, it's 1 and 2 that you cannot have. 1 by the same argument as before, and 2 by the argument that we just said. But again, just to emphasize, order would mean that in my material, everyone is pointing in the same direction. So something like this, right? This is what I will call order. What we are saying is that these configurations will be suppressed compared to ones where I have some, right. It's a bit funny, so let me not draw what's inside here, and then here everyone up. Okay. So you start with everyone up, and here you flip the puddle, you flip a big bunch of spins, and now you have here a domain where almost everyone is down, and then they change smoothly to up. And when I say down, it could be down or it could be any other direction, which is not the same as the one outside. Okay? And that would be favorable, that would be favored. So if you start with the two-dimensional magnets would not work because of that. They would just prefer to be random, and they would not preserve order. So if there would be order here, it would mean that symmetry would be broken. Because we had many directions, they were all equivalent, but we chose one. Because, for example, we applied a magnetic field and then we turned it off. Or because we chose boundary conditions, right? Or because the wind blew and slightly pointed them in one direction. So then symmetry would be broken. If, on the other hand, there is no order, means that symmetry is preserved. Yes?
Does that statement, the non-breaking of the spontaneous symmetry, does it hold for all boundary conditions in 2 dimensions?
Yes. In well, yeah. Yeah, there are some very exotic things that I'm thinking now, but I don't think they apply to this. I'm tempted to say yes. You see here, boundary condition is just a way of slightly breaking the symmetry to say that although there are all these vacua, maybe I prefer one, right? But this is also true even without boundary conditions. If I consider a big domain, right, I could just imagine that it's preferable to just pick one direction or not. And that, I think this argument is totally general. In 2 dimensions, you don't want to preserve order if you have a continuous symmetry, because it's always easy at a very low cost of energy to create bubbles. And entropy, it's still very big because it's the same computation as before. So whereas the entropy doesn't change, the energy is now very easy, if things are continuous, to create bubbles that cost very little energy.
I guess there could be some interesting things one could do with non-trivial boundary conditions, or namely topologies of the space. So, for example.
So I'm not saying that there are no phase transitions in 2 dimensions or interesting things. What the statement which is true is that you cannot have an expectation value for an order parameter. So you cannot say that I have my order parameter that chooses to go to a particular direction. That I think is true. Even if you put some crazy, I think, topological identifications in the bulk, why wouldn't you create these puddles, right? Now you could have other kind of excitations, other kind of interesting physics, like vortices and other things that I might discuss later, but that's more sophisticated. For now, I'm just talking about what I'm talking about.
So for like a 2-sphere, you have a non-trivial lower bound on the energy that that the state could have by the Harry-Ball theorem.
What is that theorem? I don't know what that theorem.
On the 2-sphere, for example, any smooth vector field must vanish at generically at least 2 points.
Yeah.
So you have to have 2 vortices.
Exactly. Yeah. Right. So let me not discuss. Let me not discuss that, but we can come to that later about vortices. I might discuss it in a few classes. Okay. So I think for most people that's a bit too fancy for now. So let me just make a general comment now. So.
You just raise the middle board, please.
Yeah. This one, right?
Thank you. Thank you.
What about the characteristics of the group that you're considering?
Right. Good point. In the same way that I made this remark, that what we said that should be very general. What matters is some discrete symmetry, and here the same thing. What matters is that you have some continuous group. If you have some continuous group, if things are continuous, and if you have some local model, you can always say that over a strip of length L over 10, I will smoothly change my configuration. So the derivative of the field would be of order 1 over L. So if I have some derivative square interaction, it will be of order 1 over L squared. And the fact that it's a vector rotating smoothly, or if it is another group element changing smoothly from one group element to another, whatever. What is important is the fact that it's continuous and that there are L units where it can change of order 1, so the change is of order 1 over L. And therefore the change square is of order 1 over L square, and therefore the total energy is of order 1. So again, it's totally general, meaning that you cannot have any symmetry breaking for any group in 2 dimensions.
Even if the group is not bounded?
Even if the group is non-compact, right? So you are asking, instead of being GoN, let the group be non-compact. So let me try to see what could go wrong there. So you are saying non-compact. Okay, now yeah, I would have to think. If I say something very quick, there is a chance that it could be wrong. So yeah, that's what could, yeah, that's a good question. If you have something in mind, come and tell me at the end. Yeah. But again, that's well beyond what we could imagine in this kind of tables. Right? Very good, but that's an excellent question. Okay. So let's try to see it. I'm sorry, I'm going to finish in 5 minutes, but I do want to do this small exercise. So I would like to try to understand. So these were heuristic arguments. Well, let's try to understand what would go wrong if we try to assume that we have spontaneous symmetry breaking. Let's try to see what happens when I have my table and I have this Mexican head potential and I expand around the vacuum. Right? So that's an important exercise. Let's do it slowly. Let's say that I have my potential that depends on my vector y, which is m squared over 2 y squared plus g y squared square. And I will pick a vacuum. So let me pick y to be equal to, let me go to the minimum of this potential that we computed somewhere there. At some point, the minimum of this double well potential. So let's see. So it is derivative, takes a 2, takes a 4. So it goes to m over 2 square root of g times, and then I pick one direction, say I point in, say, direction 1, and then I could write here. Okay, so this could be my classical configuration. And I will try to parameterize my vector y. So this is an attempt. In the following way, I say that this should be, a nice parameterization should be something like this. This is the overall size of the vector. And then the remaining components of the vector, let me call them z. So these z are n minus 1 components. Right? And what I want to say is that my vector y will want to be here at the minimum of my potential. So y squared will want to be equal to this. So this value is very close to 1. So these guys are small fluctuations. So this vector would be something like square root of 1 minus z squared. So we start around 1. Now we have here a unit vector where I have n minus 1 components, and then this vector is almost 1, but a little bit less than 1 if the other guys start fluctuating, right? So another way we could do is just take this and write. We could also repeat the same exercise with y equal y0 plus z, and z would be fluctuations. And the mathematics will be a bit different. This looks more complicated, but the mathematics are simpler here, as I'm going to explain. But if this is definitely, I agree with you that this looks conceptually simpler. So if you want, I can show you how to do it in this way. But it's just mathematics. Both represent fluctuations around this particular vacuum. And therefore, this term here is what? Is 1 minus z squared over 2 plus dot, dot, dot. And my action would be, if I plug this and study to quadratic order in Z, it would be just 1/4 of the sum over n and L Zn minus Zn plus L squared. Okay? So I leave it as a simple exercise to expand, but let me explain the intuition why I know this result is correct. Okay, actually there might be some constant here, but it's not important. But what's the intuition here? The intuition is that I have some Mexican hat here, and I'm expanding, and these are these directions here, right? But what is the mass of these directions here? Well, this one is massive because it costs energy to go up and down. But these ones are in a flat direction of the potential, right? In the figure, there's only one. But here, there are n minus 1 flat directions, right? Directions that don't cost any energy. They just move along the bottom of the potential. And therefore, these guys have m equals 0. And therefore, they only have the interaction term. Right? The m effective would be 0 for those excitations. But it's just a simple exercise to take this y, plug it into the action, expand, and see that all the masses cancel because we expanded around the correct minima. If you have a mistake and you put a 4 here, of course, it doesn't work. But if you expand around the right minima, it works. So if it doesn't work, it's because I computed this too fast. So be careful. In fact, I probably did. Yeah, for example, no, it's okay. Okay, this looks good. Yeah, it's probably not good. Probably there is an I here. You remember m squared was negative, so m is purely imaginary, so I times m is real. So probably there is an I. Right? I take it y squared is equal to minus m squared. So y is Im. Okay. And that means that this would be the action describing this fluctuation. Right? So let's estimate, therefore, the expectation value of this first component, the one we said it's in the vacuum 1. What is it? Well, it's 1 minus a half of the 2-point function of z with z. You agree? What's the 2-point function between z and z? It's a Gaussian integral. So we already computed it. It's probably, well, it's not. It was in the beginning of the lecture. But let me write it. It's the integral d dk over 2 pi to the d 1 over k squared plus 0 at small k. That's the region that is going to matter. So at small k, there was some 4 sine square of k, so it's just k squared plus 0 because there's no mass. Because these guys are massless. And, okay, there is some factor here, so there is some constant down here. Remember, in the Gaussian integral, whatever appears there appears inverted once I compute a propagator. So whatever number appears here will appear here. And also it's a different number prime because it comes multiplied by this factor here. I want to take really the fluctuations. So there is some numerical constant. And it says that it's 1 plus some small correction. Okay, it's actually just 1 plus some small correction. Right? The problem is that this small correction is not small if d is equal to 2 or 1. Because you see that this term is finite if d is bigger or equal than 3 and is divergent at k going to 0 when d is equal to 1 or 2. So we tried to say things order. Things are 1 plus small fluctuations. And then we went to see, okay, let's compute these small fluctuations, this correction to this small fluctuation, right? We tried to compute it. And what do we find? We find that it blows up in the equals 1 and 2. What does it mean? It means that in 1 and 2 dimensions, this assumption that it was pointing in one direction plus a small fluctuation was wrong. But in higher dimensions, it's okay. And that goes in line with what I was telling you. That in higher dimensions, it's fine. You can indeed go to a vacuum, and then you could have a systematic controllable expansion with small fluctuations. You cannot do it in 1 and 2 dimensions. Okay? So that's the fact that this is divergent is just a statement that we have no spontaneous symmetry breaking in 2 dimensions. And again, by universality, this same kind of analysis that we did here for a table would apply for a magnetic model where I have a lattice, where at each side I have a spin that points in some direction. And that spin is a continuous now variable, right? And the spins interact with each other with an S dot S interaction, right? And exactly the same, it will be exactly the same universality class. And that's why magnets in 3 dimensions, indeed, they could point in some direction and stay there, right? And then when they stay there, you take the magnet, you paint the first half red, the first half black, and you sell it, right? And it's there, pointing in some direction. But you cannot have this in 2 dimensions. If the magnet was really thin, it would you would paint it red and black and put it in the box, and it would already be all screwed up, right? So, but if it was in 4 dimensions, you could also do it. In 26 dimensions, we can do it, which is good for string theorists. So if we so in 26 dimensions, we could have magnets as well. Okay, so tomorrow, I'll just conclude these remarks, summarizing these symmetry breaking patterns, which is something very important. But tomorrow, it will be mostly mathematical. We will thermalize the quantum table now, going from classical to quantum. And today, you see, you have all these general heuristics, and it would be nice to have a model that would be exactly solvable, and where we would try to see these things, that fluctuations could exist, or that fluctuations would diverge, and so on. So today, in the tutorial, you solve exactly this model in the limit where n goes to infinity. It turns out that when n goes to infinity, where you have infinitely many degrees of freedom per side, this model is exactly solvable. And in the tutorial, the idea is you will solve this model, and you will then compute the exact propagator with all thermal corrections, all Feynman graphs, you can resum them all, infinitely many. And you compute this exact propagator, and you ask, can I tune the parameters to make this propagator have an effective mass 0 and have a consistent massless limit where the correlation length diverges? And you will see that yes, you can do it if d is bigger than 2, and no, we cannot do it when d is equal to 2. And that exactly is in line with what we have seen here. Okay? Cool. Oh yeah, see you tomorrow.